Good afternoon, my dear students. I will continue the Raman spectra. I will continue the Raman spectra of what is called the rotational vibrational Raman spectra for diatomic molecules. The topic is the rotational vibrational Raman spectra. Raman spectra for diatomic molecules. Diatomic molecules. So, what is the rotational, the vibrational Raman spectra for diatomic molecules? Like for example, nitrogen, chlorine, oxygen, or we having any types of molecules, diatomic molecules. So they can choose what is called as a rotational vibrational spectra for Raman for the diatomic molecules. So for this the gaseous molecules, delta nu is equal to a plus or minus 1 and delta J is equal to 0, plus or minus 2. Delta J is equal to 0, plus or minus 2. So that is delta nu is equal to a plus or minus 1 and delta J is equal to 0, a plus or minus 2. Now, it shows that is the Raman spectra for the rotational, the vibrational spectra of these molecules. So, first of all, we should draw the diagram, then you can come to know that how it forms the rotational vibrational spectra of Raman spectra. So, that is here there are some lines. And this is 7 energy levels. So that is here J is equal to 0, J is equal to 1, J is equal to 2, J is equal to 3, 4, 5, J is equal to 6. Here also same, J is equal to 1, 0, 1, 2, 3, 4, 5, and this is J is equal to 6. J is equal to 6. So these are all the spectral lines. Will be having a nu is equal to 1, and it will be having a nu is equal to, that is frequency is equal to 0. So now this is the first from the 6th energy level it will be jumped to the 4th energy level. 1, 2, 3, 4. Fourth. The next is the next will be the next. And the last one is, these are all the spectral lines. Then number 1, second, this is a third, this is a fourth, and the fifth line with a fifth line, and this is a sixth line with a sixth line. These are all a spectrum lines. Next, sixth bit, the sixth. Then first, then this is the second, and this is the third, so these lines will be called as delta J is equal to a plus 2, and then these lines are called as delta J is equal to a minus 2, and these lines will be called as delta J is equal to a 0. Delta J is equal to a 0 is delta J is equal to a 0. So it forms what is called as delta J is equal to 0, that is Stokes lines, that is called as the Rayleigh's lines. Delta J is equal to minus 2, that is Stokes lines. Delta J is equal to a plus 2, that is called as anti-Stokes lines. Here, so this is the first delta J is equal to 0, the electron present in this energy level. J is equal to 1 will be excited to, that is the delta J, nu is equal to 1. So these are the different electrons will be excited to different high energy levels. It forms what is called delta J is equal to 0. These lines will be center, it will be called as Rayleigh's lines formed in a rotational vibrational Raman spectra of diatomic molecules. In the rotational vibrational spectra of diatomic molecules of Raman spectra, it shows Rayleigh's lines, the Stokes lines, and anti-Stokes lines. The Rayleigh's line is delta J is equal to 0, that is center is all these lines will be called as the Rayleigh's lines, and towards the left side there will be forms of what is called as the Stokes lines. The Stokes lines means this is 1, 2, 3, 4 and 5, the Stokes lines, and anti-Stokes lines, that is 1, 2, 3, 4 and 5, all these lines will be called as the anti-Stokes lines. For the anti-Stokes lines, the Raman will be observed that you can say that delta J is equal to plus 2 means that they will be called as anti-Stokes lines. If delta J is equal to minus 2 will be called as Stokes lines. Okay. So now we shall come across these delta J is equal to minus 2 will be called as S branch. Then delta J is equal to 0 will be called as O branch, and Q branch, and delta J is equal to minus 2 will be called as the O branches. So now this is what is called a Raman spectra. Is that the lines will be called it as a Q branch. This is called as a Q branch. They will be called as the O branch, and then finally these are all called as S branch. S branch, this is what is called as the wave number. This is called as the wave number, that is nu bar. This one is. So this is called as a rotational, not vibrational. Raman spectrum for a diatomic molecules. The rotational vibrational Raman spectra for diatomic molecules. It also shows what is called as delta J is equal to 0 will be called as the Rayleigh lines, delta J is equal to minus 2 will be called as the Stokes lines, and delta J is equal to plus 2 will be called as the anti-Stokes lines. At the center they will be called as the Q branch lines. These lines will be called as Rayleigh lines. They will be called as Rayleigh lines, that is delta J is equal to 0. That is the intensity of the intensity of incident light is equal to the intensity of a scattered light. The intensity of the scattered light is equal to intensity of incident light. That will be called as the Rayleigh lines. Those lines will be called as a Q branch, and here the O branch lines means they will be called as the Stokes lines. Stokes lines means their intensity of incident light is always greater than that of intensity of the scattered light. Those branch lines will be called as a O branch, and S branch means they will be called as anti-Stokes lines. These anti-Stokes lines, their value is delta J is equal to plus 2, and for this one delta J is equal to 0, and this for delta J is equal to minus 2. So totally it forms the O branch, the Q branch, and S branch is there. The Q branch is delta J is equal to 0, they will be called as the Rayleigh lines, and the next is S branch will be called as that is anti-Stokes lines, and O branch will be called as that is the Stokes lines in the Raman spectrum. That is a pure rotational vibration, the Raman spectrum of diatomic molecules in the gases. The next will be come across what is called as the equation for what is called as the rotational vibration spectra of diatomic molecules. For the diatomic molecules. So that is the first one is for delta J is equal to 0. The first one is delta J is equal to 0. That is delta nu bar is equal to the omega suffix E into 1 minus 2x suffix E. So these will be called as a Q branch. They will be called as a Q branch. Then for delta J is equal to plus 2. This is a delta nu bar is equal to, that is omega E into 1 minus 2x suffix E plus what is called as 4j plus 6. So these lines will be called as the S branch. They will be called as the S branch. Then finally for delta J is equal to a minus 2. Delta J is equal to minus 2. That is delta nu bar is equal to omega E into 1 minus 2x E minus of B into the minus of B into 4j dash plus 6. So these lines will be called as the O branch. They will be called as the O branch lines. So here the Q, S and O, where is these lines, the Q, S and O, the branch will be called as the delta nu bar. The delta nu bar Q, the next is delta nu bar the S, and last one is delta nu bar O, the Q, S and O, so respectively, and the wave numbers of the exciting the light, that is so here the first one for delta J is equal to 0, that is Rayleigh lines, delta nu bar is equal to omega E into 1 minus 2xe. These lines will be called as Q branch. They will be called as Q branch means Rayleigh lines. The next is for delta J is equal to plus 2 means it will be called as anti-Stokes lines. Nu bar is equal to omega E into 1 minus 2xe plus B into 4j plus 6. These lines they will be called as S branch, the lines. These lines will be called as anti-Stokes lines of a Raman spectrum. Then we will be having for delta J is equal to minus 2 is delta nu bar is equal to omega E into 1 minus 2xE minus B into 4J dash plus 6. So that is here, this is called as the O branch lines. So these are all the spectral lines formed in the what is called as rotational vibration, the Raman spectra for diatomic molecules of the gases. The next, the final equation for this one, the rotational vibration, the Raman spectra is in the next step, write down and nu bar suffix q is equal to nu bar I minus delta nu bar q. Then nu bar s is equal to nu bar I minus delta nu bar the s, and nu bar o is equal to nu bar I minus delta nu bar suffix o. So these lines will be called as the Stokes lines, anti-Stokes lines. For those delta nu is equal to minus 1, usually the weak. So that is Stokes and anti-Stokes lines are very weak is there. So these are all the equations. Nu bar q is equal to nu I minus delta nu bar q is there. Then the second one, nu bar s is equal to nu bar I minus nu bar delta nu bar s. The nu bar suffix 0 is equal to nu bar I minus delta into nu bar O. So these are all called as the rotational and vibrational Raman spectra of that is for diatomic molecules, for the diatomic molecules. Then what is the advantages of a Raman spectra over that is infrared spectroscopy for the infrared spectroscopy? So here the Raman spectra will be forms, the first point, Raman spectra forms a spectrum in solids, liquids and gases, but in the infrared spectrum it forms only the solids and liquids are in quite diffused state, The first point is this one over Raman spectra and infrared spectra. This one is there. The Raman spectra shows a spectrum in the solids, liquids and gases, whereas infrared spectra shows only in the solids and liquids that in diffused light. The next second point, since the Raman spectra are independent of the Rayleigh's lines, incident radiation, by suitably adjusting the frequency of the incident radiation. Raman spectra can also be obtained in the visual spectrum range, where they can be easily observed rather than the more different of what is called as infrared ranges. In the infrared spectrum, we cannot observe any spectral lines, but in the Raman spectra, we can observe either the Stokes lines or the anti-Stokes lines. Anti-Stokes lines are having, that is one. Last one is the Raman spectra can be obtained, even the molecules of the Raman spectra can be obtained the oxygen and nitrogen and chlorine molecules, but this cannot be formed in the infrared spectroscopy. Thank you, Mananda. I will complete this one.